Okay, so this video is to talk about this quiz where we had some problems. Let's start with what the correct answer was and what I would have expected in a correct answer. So, the the question asked which of these Lewis structures is or which are the most stable Lewis structures for the sulfate ion and why. Okay. What three factors help you determine ion stability? Sorry, I'm having trouble seeing the actual camera and what I'm writing and where. Okay. Which of these, what are our factors that contribute to stability when resonance structures are involved? First of all, there we go. Okay. First of all, we have to think about formal charge. What do we have to think about with formal charge? We want negative charges on the most electronegative atoms and we want positive charges on the least electronegative atoms. So vice versa. Okay, this means that my most electronegative atom needs to have negative formal charges as opposed to the less electronegative atoms, because my more electronegative atom can stabilize more easily with extra electrons there. Okay, or with a negative charge there. Why is that? Because my more electronegative atoms will be the ones that have a greater tendency towards stability with more electrons on them. So if they are the ones carrying a more negative charge, they will be more stable than the less electronegative atoms that don't take negative charges very well. Okay, what else do we have to think about with formal charge? We have to think about having the we have to think about having the lowest possible amount of deviation from zero. Or in other words, we want to have the maximum possible number of atoms with lowest possible charges. Now, when I was grading the quizzes, something I saw here was that a lot of people remembered this rule when they were picking which of our Lewis structures were the most stable. What they forgot was this first rule. And as it turns out, this first rule is the one that is more important to stability. Okay? This one is the one that is more important to stability. So, we also want to make sure that all of our formal charges add up to the overall charge on the atom, no, not atom, sorry, ion or molecule. We want to make sure that all of our formal charges add up to having the same overall charge as the charge on our ion or on our molecule, depending on what we're looking at. Okay. The other thing we had to keep in mind was the octet rule. Obviously, we know that atoms are most stable with a full octet, especially when we're talking about atoms in the first period. Okay. Atoms in the second period, if they're in the p subshell, can tend to have the possibility, at least, of having expanded octets because of the d orbitals that are accessible to them. But for everything in the first period, we're going to see obedience to the octet rule being the most stable option. Most of you remembered on the quiz that carbon is most stable with 4 bonds, nitrogen with 3 bonds and 1 lone pair, oxygen with 2 bonds and 2 lone pairs, and halogens with 1 bond, 3 lone pairs. Obviously, the only one of these that came into play here was the oxygen one, because on our quiz all we had were oxygen and sulfur. Some of you forgot, though, that sulfur, which is directly below oxygen on the periodic table, can have a expanded octet because of the accessible d orbitals that sulfur has. Okay, so when we are looking at stability of a Lewis structure, these are the things that we have to keep in mind. That means that now it's time to actually take a look at the quiz and figure out, okay, so using these things to keeping these things in mind, which ones of these are the most stable? Okay. If we look at answer choice A, we can calculate the formal charge on each one of these atoms. Okay, oxygen with a double bond has a formal charge of 0 because there are 1, 2, 3, 4 electrons belonging to oxygen, 4 non-bonding electrons, and it gets half of the bonding electrons, so basically this half of the bond. Okay, so oxygen has 1, 2, 3, 4, 5, 6 electrons here, and we know its valence minus number of bonding electrons times 1/2 plus number of non-bonding electrons. Please don't get non-bonding confused with anti-bonding from our molecular orbital theory. Okay, they're not the same thing. Anyway, oxygen with 2 bonds and 2 lone pairs is going to have a 0 formal charge because it has 6 valence electrons, and there are 1/2 times 4 bonding electrons, so 2 plus 4 non-bonding electrons. 6 minus 6 is 0, so we can go through this page right now, and every time we see an oxygen with 2 pairs, 2 bonds and 2 lone pairs, we can mark that it has a formal charge of 0. Okay. Now, oxygen with 1 bond and 3 lone pairs. This is a possible configuration for oxygen. It's not impossible, it's just less stable. we see that we have 6 valence electrons minus 2 bonding electrons times 1/2 plus 1, 2, 3, 4, 5, 6 non-bonding electrons. So we've got 7 in here, 6 valence electrons, 6 minus 7 is -1. So we know every time, and this is true all the time, not just on this quiz, but every time oxygen has 1 bond and 3 lone pairs, it's got a formal charge of -1. And we can mark that on the paper every single time we see an oxygen with 1 bond and 3 lone pairs. Okay, now there are, oops, I missed one. There are 2 times on this paper where we see oxygen with 3 bonds and 1 lone pair. Again, it's possible. It's not very stable, but it is possible for that to occur for oxygen. Because it's so unstable, it's not going to stay that way, but it's possible that we could see this happen. And if we take a look at our formal charge here, we'd see that the number of bonding electrons here is 246 times 1/2, so 3, plus the non-bonding electrons on oxygen, 3 plus 1, 2, so there are 5 electrons on my oxygen here, and there's a valence of 6, so 6 minus 5 is +1. I could mark that on both of these. Okay. I said that 3 bonds and 1 lone pair on oxygen is really unstable. The reason that that is really unstable is because that gives oxygen a positive charge. And oxygen, if you take a look at a periodic table, oxygen is the second most electronegative element. It's right next to fluorine. Okay, so right off the bat, when you see that oxygen has a +1 charge here, and that there are possible answer choices that don't have oxygen with a positive charge, you can go ahead and say, okay, I know that this can't possibly be the most stable answer. There is no way that oxygen with a positive charge is going to be stable enough to even compete with these other ones. Now let's take a second and look at sulfur. How many valence electrons does sulfur have? It has 6, but it is possible for sulfur to have an expanded octet. So sulfur can be stable with 6 electrons around it, but it can also be stable with 10, which was one of those expanded octet exceptions that was mentioned in the chapter that you were supposed to learn. So if we take a look at sulfur, we can see that this sulfur has 2, 4, 6, 8, 10 electrons around it in these bonds. And we know that that is a stable configuration for sulfur. So we know that we're okay here. Okay. And anytime that sulfur has 1, 2, 3, 4, 5, 6 bonds around it. Wait. No, I was counting wrong earlier. Same idea though. Sulfur can still expand to having 12 electrons around it for the same reason, d orbitals. Okay. Anytime we see this sulfur with 1, 2, 3, 4, 5, 6 bonds around it, we know that we're stable, we're fine. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Ooh, let's come back to that. 1, 2, 3, 4, 5, 6. Sulfur's fine, although we already figured out that those two were bad, so I don't know why I even bothered. 1, 2, 3, 4, 5, 6, 7. Ooh, come back to that. 7, we'll come back to that. 1, 2, 3, 4, 5, 6. Okay. If we have 7 bonding pairs around our sulfur, then what we have is 1, 2, 3, 4, 5, 6, 7 times 2 would be that there are 14 electrons around sulfur here. and half of those would be 7. Sulfur has 6 valence electrons, so 6 minus 7 would be -1. This gives us a negative charge on sulfur each of these times where sulfur has 7 bonds around it. Sulfur is much less electronegative than oxygen, in a relative sense. Okay, oxygen is definitely more electronegative than sulfur is. So it is not very stable for sulfur to have these negative formal charges on it. Anytime that the molecule or the ion would get pushed into these configurations, the electrons would move back around to restabilize. They'd get further away from all these other electrons that are repelling them, and they would move back into a configuration where sulfur would have a 0 formal charge. Okay, so that means that I can roll out F and G and D as being viable answer choices because sulfur has a positive formal charge on those. This leaves me with 3 answer choices, A, B, and H. There were quite a few people who suggested that H was the one most stable thing here, because in H we see that the electron repulsions are minimized by being on opposite sides of the sulfur. People who said that were not taking VSEPR into account. When you have something with a central atom with 4 electron domains around it, you have a tetrahedral molecular structure. Okay? And in a tetrahedral structure, if you rotate this around, it doesn't matter which way you rotate it, all of these atoms on the ends are the same distance from each other. Just because one is at the top and 2 look like they're across from each other doesn't mean that's what it actually is. I can rotate this in as many directions as I want, and I could end up moving it, like I could move this one down here. That would move this one up to the top. I should have drawn this further apart, sorry. That would move this one here and this one here. But they're the same distance from each other now, even though they're in a different conformation. Okay, so people who said that was not bad thinking, but the truth is that these are all equally far apart in space, and that is something you have to keep in mind. Okay, so to get what I would have wanted to give full credit for this question, you got a point for knowing that the most stable ones were A, B, and H. If you answered A, B, and H, you got point. Okay, that was 3 out of the 4 points on this quiz. If you told me it was only H and you gave a decent explanation of it being because these electrons were far away from the molecule from each other, I gave you partial credit because I think if you had taken VSEPR into account, you would have gotten it right. Okay, so this was a quiz out of 4 points, but some people got 5 points, and this is only 3 points. The other place you got points was you got 1 point for giving me any one of these reasons as a correct explanation of why you picked your answer choices. Okay, and the extra point, the bonus point, was if you mentioned resonance structures. Now, this was not my ideal rubric for this quiz. Okay? What I wanted to do, but if I had done this, everyone would have failed, What I wanted was to give a point for A, B, and H, a point each for those. And I wanted not just a point for one explanation, and not just a bonus for mentioning resonance. But what I really wanted was for you to give me all of this. You didn't have to give me each reason why each one of these was wrong, although you could have done that. But what a complete answer would be to tell me that in A, B, and H, the negative charges are on the most electronegative atom. There are no positive charges on the most electronegative atoms. You have the least deviations from zero possible, meaning you've only got 2 atoms that are non-zero formal charges, and they're very small absolute values on them. You should have, an ideal answer would have also mentioned, in addition to that, that the formal charges on each one of our atoms add up to -2, which was the charge on our overall ion. An ideal answer also should have mentioned that the octet rule is fulfilled for the maximum number of oxygens possible while still keeping our electronegativity rule in mind, and that sulfur is still stable because it has an expanded octet. Okay, all of those things should have been mentioned if you had really answered this question well. Additionally, everyone should have mentioned resonance structures. I don't know why some of you guys didn't even mention it, because it is extremely important to note that these are all possible resonance structures for the sulfate ion. Okay, every single one of these could exist at any one moment in time. It wouldn't be very stable. It would move back to a more stable configuration for some of these, but it is possible for all of these to exist. And the true, in real life, sulfate ion looks like a combination of all of these. Okay, it lies more heavily toward looking like A, B, and H, but there are kind of little twinges of the other ones in there, because these are all resonance structures. Okay. That should have been the first thing you said, really, is that A, B, and H are all equally stable resonance structures. Side note, it is resonance structures, not resonant, although I gave you the point anyway if you said resonant. Okay. In chemistry, this is not a thing. Don't write it. Okay. Resonant structures are not a thing. They are called resonance structures. The singular of resonance structures is resonance structure, not resonant structures. Okay. All right, that's all I have to say on the matter. Please leave a message in the comments telling me that you did watch this. Also put your name, since most likely I'm not going to be able to tell from your YouTube account handle who you are. And if you don't want to make a YouTube account, you can turn in a summary to me of this video tomorrow. Thank you for your time. Good luck on the test. Study. Ask me questions in the comments if you have them. And I'll see you tomorrow.